meet you, even though online, and talk a bit about offshore wind and grids. And keeping a bit in mind, now that I see that Kaushik went a bit over time, I start thinking maybe I was a bit too ambitious also with my own presentation and slides, but let's see how it goes. But my idea today was to talk a bit about offshore wind in general, and then introduce to you a bit the electrical concepts for the collection and the transmission of offshore wind, and then focus a bit more on the transmission and grids development for offshore wind, and finally maybe say a few things about the trends when it comes to offshore wind grid integration. But before that, just very briefly about myself. I think Anka said it a bit, but I kind of like to show this picture. So I will say again that I started as working on wind turbine electrical control many years ago, but in the last years I've been focusing much more on offshore wind, so more system level aspects on offshore wind, grid integration, and HVDC and electrical infrastructure design. And I also do supervision and teaching at master students and PhD level. And I think we have our own experience with ITN networks, but I think it's a very, very nice project. Hard to get, but once get it, it's a very nice project to have always a nice group of talented young people doing PhD projects at the same time. Now, beyond that, moving that a bit, you probably have seen that or heard about it, that Denmark is a wind energy nation, and actually wind in Denmark represents maybe much larger than it's seen at first with 1 out of every 50 employees in the private sector being employed by the wind turbine industry. And maybe the numbers have changed a bit, but I think the image is still the same. So wind is representing a big part of the total Danish export system, but also Denmark is the country with the highest share of wind energy in its electricity demand. And I know that at least Damian is part of this group, and I don't know if he's now here, but in normal conditions he will say something about Ireland. But I do think that Denmark is still a bit above Ireland when it comes to share of wind power. So Denmark has been from the beginning one of the leaders in wind power, and this is the same in offshore wind. Actually, the first ever what we used to be called offshore wind farm, and I am hesitating a bit to call it an offshore wind farm because, as you can see in the picture, it's very, very, very close to the shore. Today, definitely this will not qualify as an offshore wind power plant, not even a near coast one. I think it's very, very close, but it was built already in 1991. Was even decommissioned in 2017. So it has actually reached its lifetime, and it had a total installed capacity of 5 megawatts, and they used 11 wind turbines for reaching this capacity. But beyond that, the very first ever offshore wind project, Denmark also is home to the first 2 very large hundreds of megawatt scale offshore wind farms, Consortium 1 in 2002 and Newstead 1 in 2003. So Denmark has also been a leader in offshore wind, and it's also home to probably the most shown picture ever when you talk about wind energy in general, and especially when we talk about offshore wind. And there's a second one, but I think the one on the left from Consortium 1, it's probably, as I said, the most shown picture, and not only because it's spectacular and it's visually it's very nice, but also because it shows a very interesting topic, very important topic in wind energy in general, the fact that wind turbines do interact with each other through their aerodynamic, through the flow inside the wind farm, and they have an aerodynamic interaction. So what you can see here is how the wind behind the wind turbine is behaving and is impacting the other wind turbines. I will not say much more about that, but I thought it's interesting to show this well-known picture. And there is actually a paper analyzing the conditions under which this picture was taken. But Moving on, when we talk about offshore wind, you probably, I don't really know your individual PhD projects, but I would be surprised that at least a few of you are related to offshore wind. And in general, when we say offshore wind, we say that offshore wind is big. So when we talk about how big is offshore wind, you can see here newspapers. This is a newspaper in Denmark. It's in Danish, but that's not relevant, the text, but it actually shows one of the Bourbon extension, an 8 megawatts wind turbine, and it's comparing it with a Vindeby, which is what I showed you a couple of slides back, the very first wind farm built in Denmark, and how much larger that is. And if you can see that back then, and this is, if I can see, in 2016, so only a few years back then we were still comparing wind turbines to the what I think it is the largest airplane still, passenger airplane in the world, the Airbus A380, and trying to compare to give a sense of the size of the wind turbines. But in the meanwhile, things have developed even further, and this slide is actually a bit outdated already. Myself, I should update that, but now we already have the Gilead, the GE Heliade wind turbine with 12 megawatts, which when we try to compare it, of course, comparing it to an airplane, it's already way obsolete. So it starts being compared to truly magnificent and large structures like the Eiffel Tower and the Shard structure, which I think it's in London. And not only that, but already, as I said, this 12 megawatts wind turbine is obsolete because I think, if I'm not very wrong, Vestas already announced a 15 megawatts wind turbine, which is already more than double the size of this Bourbon extension a few years ago. So when we talk about offshore wind turbines, we talk about really large structure. I think it's they probably the largest rotating machines in the world right now are offshore wind turbines. But then also when we talk about offshore wind, we also talk about how large is large, and to get a sense of what it means of an offshore wind project in terms of geographical spreading. You can see here an illustration of the Dogger's Bank project, which when completed will have three different wind power plants with 3.6 gigawatts installed capacity. But the area they are expected to cover is similar to the Greater London area. So we are not talking only about very big structures, but we also are talking about projects that are spreading over very large areas. And finally, it's not only that, so it's not only big and large, but it's also far away and further away from shore. And you can see here I think these are the statistics from 2020 from Wind Europe. It shows in 2020 the projects that were, no, this is during 2019, I'm sorry. So this is the average water depth and distance from shore for the projects that were under construction in 2019. And you can see that the distance is going further and further. We're already having projects that are built or were built 2 years ago. A distance is further than 100 kilometers from shore. And if we want to see an image in general, you see here the rolling average distance to shore of online offshore wind farms. And you can see that while it has been for quite some time, it was fairly close to shore. This is below 20 kilometers from shore. We already have a very steep increase in the last years, and this is average. So to get this steep increase means that the new projects are coming much further out in the North Sea or in the sea compared to the previous ones. So we have a very steep increase here, almost doubling from the distance to 60 kilometers on average. And I think that's very important because it plays a very big role in the transmission, grid connection and transmission for offshore wind. So hopefully you get the idea that offshore wind is really big business in all directions right now. And there are still aspects that I haven't covered here, but the good part, or what, as we all know, is that offshore wind has known a very large or very steep increase in popularity and in installed capacity, and this happened basically or mostly because of the very important cost reductions for offshore wind. You can see here in a graph there was the envelope, the bluish color, whatever this color is, the shaded one. It shows what was the estimates of, I don't know, I think over 150 or over 100 experts from all over the world were asked to give their estimates about the cost evolution of offshore wind until to 2030. And then you have with the different colors the actual cost or the actual LCOE costs that were bidded for in the real projects. And you can see that experts were way far out because cost reductions even higher than what they were expecting by 2030. They already happened in 2020. So there was a dramatic, really dramatic drop in the cost of offshore wind, and that is very good, of course, and will help in the future or continue this and even accelerate this trend for development. But if we look a bit closer, the main drivers behind this cost reduction are coming from technology innovations in wind turbines, what I was showing a bit earlier, larger and larger wind turbines, and also in streamlining the installation process, as together with the fact that the financing is cheaper. So when we look at what we are interested in, the grid connection part, here we can see that the grid connection, which is in this graph from TenneT a couple of years ago, but in this graph is shown with a yellow color. It's not only has not really changed its value, but or has not decreased, but it actually has a tendency to increase in cost. So a grid connection for offshore wind is one of the areas where not really much cost reduction have happened. And of course, there will always be limited cost reduction you can do, especially when we are moving further away from shore, because simply the distance from shore it plays an very important role in, or it's one of the very important cost driver for the grid connection of offshore wind. Now, if we come a bit closer, and I will get back to the transmission part, but before we go that, if we look at the wind farm layouts, we can see here is an example with the three offshore wind farms in the Hornsrev area. The very first one that I showed built almost 20 years ago, and then Hornsrev 2 and 3. And we can see that while the first one was a very nice grid-based design of the wind turbines, very symmetrical, when we moved to the second one in 2009, we still have a kind of a grid-based design, but already the shape is more fluid, or it has changed shape mostly to counteract as I showed you in the picture, the aerodynamic interaction between the wind turbines. And then we have the latest one in the Hornsrev 3, which became operational a few years ago. You can see a much more kind of randomized or less grid side layout for the wind power plants. And again, this is driven on the specific conditions, maybe the seabed, maybe their locations, parts of the area where the wind farm is located. Wind turbines may not be placed, but they're also driven by the trying to minimize the aerodynamic interaction and maximizing the power production in the wind power plant. But this has an impact. I will not insist a lot on that today, but it does have an impact on the electrical, on the topology of the collection system in the wind power plants. And when we talk about the collection system, there are a few ways where we can do that. One is the very standard radial one, which you have a number of wind turbines are connected to each other, and then the whole string is connected to the offshore substation of the offshore platform. Then we have the star connection, where each wind turbine is connected to the same substation individually, and then we can have the ring kind of connection, the single or double ring, where you have where some redundancy is introduced in the connection to the offshore substation. And as you probably already can imagine, we do that to have an impact on the reliability of the plant. In this case, in the radial connection, which is the cheapest of them all, if we have a fault in this point, then everything that is behind or behind the fault is getting disconnected. So the production will suffer. All the wind turbines behind the faulted point will disconnect. If we have in a star setup, if we have the same thing, then it's rather simple, because only the single wind turbine where the fault has happened will disconnect, and the rest will continue to operate. But that, of course, means significant larger amount of cables, kilometers of cables being laid in the seabed. And then in the ring topology, of course, depending on the sizing of the cable, a fault will have no impact virtually, because the current has different paths, alternative paths to go to the substation. But of course, this is also an expensive because you have more kilometers of cables compared to the radial, but also the cables should be oversized because they should be able to carry the power produced from more wind turbines in case of fault situation. So these are the three standard topologies for creating the collection system for wind power plants. The vast majority of them today are radial, but I think there is an increasing interest towards having more redundancy, especially when we have larger and larger plants, to have more redundancy, and then looking at ring topologies for the collector system. Again, if we look a bit closer, then in the electrical single line diagram of a wind power plant, you can see that we have the wind turbines with their converter, and offshore virtually all wind turbines are type 4 wind turbines. I trust you've already discussed about, or you know about, the type of wind turbines. So they are full converter wind turbines, which then they have their wind turbine transformer increasing the voltage to the collector system, and then each radial or each string is then brought to the offshore substation, where it connects to the offshore transformer, which more often than not today also has included redundancy. So typically there are two offshore transformers with 50-50 kind of rating, or even different, a bit overrated. So in case that one transformer is out, still it can transfer amount of power through the other transformer, and all those then are connected to the shore. So I think the main characteristic here is that we typically have three levels of voltage. One level which is low voltage inside the wind turbines, then typically medium voltage levels in the collector system, and then high voltage in transmission to shore. In our case, I don't think this is a general drawing, doesn't have only offshore wind power plants, but in offshore even more, because the transmission to shore will have a more significant length. Now, when we talk about transmission for offshore wind, of course, transmitting in AC is because of the availability of the transformers and how simple they are. Transferring power in AC is the preferred way, but AC transmission is limited by the reactive current, and then you need to compensate that. This is an example of that, where you can see how a graph of how much power can be transferred over how long distance, both depending on the voltage level for the different colors, but also in having a compensation on both sides or not. And you can see that the compensation part can increase significantly the distance for which we can transfer power, but still this has some limits. And in general, anything we talk about offshore, as people used to say, real estate offshore is very expensive. So anything that has to be built on a platform in an offshore environment costs much more than in onshore. So in general, trying to build as few things as possible offshore. So when we reach these limits for AC transmission, then the alternative would be, of course, to use a DC transmission. And one of the most common question is, what is the break-even point? And by break-even point, we understand the point where the cost of the transmission switches from AC being cheaper to DC being cheaper. And you have a graphical representation of that. You can see it in many shapes and forms, but what it shows is that while the AC, the initial cost, the capex for AC connection is rather small because there are a few components, then the OPEX, or the cost related to the losses, are increasing quite steep with the distance, which in the case of DC is the other way around, where we have high initial capital cost because you have to have the transformers and much more infrastructure that needs to be built in the beginning. But then the operating costs are much lower because losses are very small in DC environment. And then we are reaching a point where this is changing. And that distance today, I think it's anywhere between 60 to 80 kilometers or even more, depending on different things. But there is a gray area where it's not very clear if AC is more expensive than DC. Moving on, again, the grid connection main components. I think I already talked about that, so I will skip it. But what I didn't show earlier is that actually when we talk about even for AC connected wind, when we look into the details, it has an electrical infrastructure which is a bit more complex than what first meets the eye. And here we have the single line diagram of the Hornsea 1 wind power plant, which I think it's still the largest in the world. This lately changes quite quickly. Which one is the largest in the world? Can somebody please mute? I have strong noise in my. Thank you. So when we look at closer, we can see that we have the three clusters of wind. Each cluster has 58 wind turbines with 12 strings. The two transformers, as I said, and then we have the submarine cable connection to shore. And you see that we have compensation on the offshore part, on the onshore part, but actually also in the midpoint in this case, because the export cables are 170 kilometers. And this, of course, as I said earlier, would probably won't be able to do it with AC connection unless you have also a midpoint compensation. So the cable is basically, the export cable is basically split into two segments, two individual segments, and each segment is compensated at both ends. And that's one way to increase the possible distance that you can transmit in AC. So we have these compensations, of course, including much more cost here for an extra offshore platform in the midpoint. So we have the compensations, but then we also have the filters because of this very long AC cables and a lot of switching elements in the wind power plant. There are resonances and harmonics and all kind of phenomena. So a lot of filtering it's required, but also it has STATCOM units which are used to provide reactive power compensation at the point of connection with the onshore system, and then of course more compensations and filters on the high voltage side of the onshore connection. So without going into details, what I'm trying to show here is that actually offshore wind power plants have already the large ones, the very large ones we are building today, have very complex electrical infrastructure with many components and many filters. If we go to the DC connection, this is high voltage DC. Sorry for the typo. Is very similar to the AC one, with the difference that you need to have two converter stations, one offshore to as a rectifier from AC to DC, then transmitted to shore, and of course on the onshore part we need to have an inverter to connect it back, to transform it back to AC and feed it into the main AC system. So, but if we stay a bit with now with the HVDC transmission, we have typically two main uses for HVDC transmission today. One is as an interconnector, so connecting two AC systems. You have this is a connection between UK and Belgium, the Nautilus one, and you have the AC system, the UK one and the Belgium one, and then we have again the substations, which in this case are both onshore, and then the DC cable between them. So we use DC connection or HVDC connections for interconnecting two AC areas, or of course for interconnecting offshore wind power plants to shore, which is pretty similar to this one, but you have on one end it's not onshore or another AC system, but it's the offshore wind power plant, which is connected to the HVDC, the offshore HVDC converter, and then transmitted to shore and connected to the main AC system. And I think I already said a bit about it, but why would we use HVDC, you saw that theoretically at least we can have a very large distance covered by AC if we have frequent enough points for compensation of that. But beyond the fact that this is becoming too expensive, actually HVDC has the fact that it needs fewer cables for equal power transmission, and maybe here I should say that the environmental concern, especially in the North Sea, is becoming bigger and bigger issue that is coming up, because more and more installing more and more offshore wind has a bigger and bigger impact on the environmental. So actually being able to reduce the footprint of the infrastructure is something that is becoming increasingly important. So fewer cables needed for equal power transmission, and then lower losses, which means that no reactive losses means you don't have stability problem. Theoretically, there is no limit to the cable length, and in general, the losses are much lower. But also, this is more constructive, if you want, but more from an active perspective, from a controllable. Being a DC can actually connect asynchronous grids, as I showed earlier, between the UK, the UK grid and the UCTE, the continental Europe one, or the Nordic in case of Denmark and Norway. But also very important, increasingly important, is that the power flow can be fully controlled. And I'll get back to that with the VSC converters. We can have full control on active and reactive power, so it can provide also a lot of ancillary services or other kind of reliability services needed for the grid. When we talk about technologies, and I will go very fast on that, because LCC, the line commutated, it's an old and very mature technology. I think it started in the 1950s, and there are quite a number of connections. Maybe not so many in Europe, but all over the world there is a large number of LCC connected or HVDC links based on LCC technology. But today, what we are using, especially in the context of offshore wind, is VSC voltage source converters for all the for a number of advantages that it has, but mostly because of the controllability that it provides. And yeah, I'll skip that. I can give you the slides later, and I also have a comparison between LCC and VSC. And I think the very important part is that it has current reversal is possible, so the flow can be reversed very quickly. But also it has a very fine reactive power control, so control active and reactive power separately, and do that with a very high precision. Of course, one of the big problems with used to be with the VSC HVDC are the losses, which are very low for the HVDC Classic or the LCC, but this is constantly improving, and I think already the losses today, this graph has been a few years old, but the losses today in the VSC systems are getting much closer to the LCC ones. So VSC converters are now, I think by far the preferred option, especially in Europe, for all the HVDC links. And how a VSC station layout looks, it's very straightforward. I think we have the DC side with a DC capacitor used to control the voltage in the DC link, then the actual converter, and on the AC side, the phase reactor of the transformer, and then the connection to the grid, to the AC grid. And as I said, the control principle, by controlling the voltage difference or the voltage difference across this phase reactor on the AC side, we can control the active and reactive power. And as you probably know very well, we control the power. The active power is controlled by controlling the angle of the voltage, and the reactive power is controlled by modifying the magnitude, the amplitude of the voltage. So we can control, and of course we can control those two independently, being able to, as I said again, to have a full and independent control on active and reactive power on the AC side. When we talk about the HVDC transmission, and this is coming back a bit, the previous one I showed either point-to-point interconnector or in relation with offshore wind. There are a number of ways of doing that. So we have the monopolar, bipolar, or the back-to-back converter, and I'll go bit quickly through it. The monopolar is the most basic one and the cheapest one. So in the very simple way of doing that, we have a ground return. So you have only one fully insulated DC cable, and the return is through the ground. Or you can have a metallic return, so still a cable return, but this cable will be with much less rated than the other lower voltage, so it will be less insulated. But the main issue with that is, of course, the environmental part when we have the return through the seabed, but also the fact that the transformer connected on the AC side will see an imbalance, because it will be a DC offset on that part. So the transformer will need additional insulation. So to avoid that, we have the symmetric monopole, which has two fully and identical DC cables, which means that things are very balanced on the AC side, but the cost is a bit higher because you have two DC cables with full insulations. And of course, this schematic has basically no redundancy, because if a cable or a converter fault occurs, then everything goes out. There is not alternative path for the current to flow. And I think today, virtually all connections, not virtually, actually literally all wind power plant connections are based on symmetric monopoles. The second one, the bipolar one, is using two converters on each side, and that will do again with ground return or metallic return. And that, of course, has the disadvantage, if you want, that it has more converters, so a higher initial cost, but it can also be used at higher power ratings, because there are still limits on the ratings of the IGBTs. So there is a limit on how much power a single VSC converter can carry. So by having two converters on each side, we are increasing this limit. But also, in case of faults, it provides redundancy, because in case of a fault, the system is still available depending on the type of fault. Yeah, so it's if it's a cable fault, we will still have you have a path through the return, which is the metallic or the ground. It can become a monopole. And the same if you have a converter, then they are simply using the cable. If there is a converter fault, you can use the connection and to use the cable to close the circuit and have only one converter on one side and two converters on the other side. So it can operate in case of faults, and this is important and very important. Maybe I was trying to say is that this can easily happen by retrofitting current existing LCC connections. So in between Denmark and Norway, we have 4 DC connections, KRAC 1 to 4, and actually the fourth one was created with a VSC, but it was created as a bipolar connection using an existing LCC. So it's one way to create a bipolar is by retrofitting it or connecting it to existing LCC connections, and then you have all these advantages. And then finally, we have the back-to-back, which is simply a converter. And maybe you can see, I hope you can see here, is not too small, the Krieger's flag connection, which is between Denmark and Germany. And these are two different synchronous areas. So while the connections is in AC, so the connections for the wind power plants to either Denmark or Germany to the shore, they are done with AC technology. At some point, since those two are different synchronous areas, this needs to be broken. And the solution chosen in this case is to use a back-to-back converter onshore here, which is simply having a DC link to break the frequency coupling between the two asynchronous areas. And then, of course, can be either monopolar or bipolar, and it's lower because it's can have a lower DC link voltage because it doesn't have a lot of, there's no transmission. It's used only for coupling and controllability. So these are the main 3 concepts when we are talking about point-to-point HVDC connection today. When we look at their control, because so far we've discussed about basic characteristics, but nothing about control. So when we look at the control of a point-to-point VSC HVDC link, this is showing between two AC systems, and of course one of them will typically control the power flow, so will control the power injected into the DC link, or the power transfer on the link, while the other one will typically try to control the DC link voltage, so maintain the DC link voltage constant. So each one of them will be one in P and the other one in VDC mode, and then both of them can control the reactive power exchange with the onshore grid. And this is happening because both of them are connected to AC grids, which are fully energized and controlled by other sources in the grid. But when we look at HVDC transmission, so connecting an offshore wind, and in this case consider that this AC1 is an offshore wind power plant, then for the offshore AC network of the power plant, somebody else has to. The wind turbines are in grid following mode, so they require to have an energized and controlled grid to which they connect, and then they just inject current synchronized with that grid. So then the HVDC converter offshore has to control the frequency or power shown here and the voltage of the AC system, and then the onshore converter typically has the same control mode, is controlling the VDC and the reactive power exchange with the onshore grid. Yeah, again, I think I already said that the offshore HVDC converter is the one that has to maintain the offshore AC network, but also can be used to provide ancillary services or being able to comply with the relevant grid codes for the onshore, the grid codes of the onshore system they are connected to. And then, of course, if we look a bit on the operational modes, in the normal operation, all it has to do is inject the power that is produced by the wind power plant to the grid, and is doing that by trying to maintain the offshore grid voltage constant. And then it's operating, as I said, in grid forming mode. And it should change mode when we have a fault or an abnormal operation in the system, a fault or a loss of grid, or something has happened. Then the HVDC network may not be able to export all the power, which also means that the voltage will increase. So a power reduction needs to happen, and this can be done by having a voltage droop mode. Finally, as I said, it needs to control to operate in grid forming control mode, and they've been doing that for quite some years now. I think the first HVDC connected wind power plants in Germany are by now I don't know, 10 years old or maybe a little more. I cannot recall, but quite some time now. So and you can do that. This can be done either in a cascaded control scheme, which means current controllers and then the outer voltage loops, or as a direct voltage control, which it's good because it forces directly the voltage. You control directly the voltage, not indirectly through the current loop. But then when you have a fault, typically it needs to switch to a current control because it needs to limit the current. Converters are very, very sensitive to overcurrent, and of course, controller design, like in all cases, is very important here because there can be several resonances between the different controllers for the wind turbines and the offshore HVDC, and I think this was learned kind of the hard way in the very first HVDC connected offshore wind power plants, where a lot of resonances were seen and significant problems were created by that. And then, of course, the protections, but that's I'll skip that part because it's maybe not. I don't want to focus too much on that part. So this is what the offshore HVDC VSC converter does in a point-to-point connection. And until now, we talked only on point-to-point connections. But if we look at the offshore wind in Europe, as I said, is increasing, and it's increasing very fast, and expected to increase even faster, to accelerate even more its annual capacity. And we can also see here that the existing projects, or the ones which are planned, are getting further and further away from shore. So that means that the technology will start playing more important role. And we already We already have quite a number of HVDC connections in the North Sea. This is a complicated, a bit complex graph, but I think it's nice because it shows actually all the HVDC connections which are existing or planned in the North and the Baltic, in the northern seas. And very quickly, what we can notice here is that all of them are point-to-points. All of them are going from point A to point B, or the same here from point N to point B. And if you are curious, I think this is a line supplying, or this one up here, it's a line supplying one of the offshore rigs, so the oil rigs in the Northern Sea. So it has an HVDC connection to be supplied from shore. But virtually, or all of those connections are point-to-point. So today, what we do is when we build or we want to connect two assets, we build a line between those 2 points. But if we take into account that the ambitions, again, I say about offshore wind are very, very high, and we are expecting to reach maybe 200 gigawatts by 2050. If we continue this way of thinking by connecting point to point, so each project is connected to the shore, we will end up having something like that. Of course, this is a non-artist or an engineer illustration of the grid, but it will end up looking way too many connections and too many cables to the shore. We have a very spaghetti-like type of connection, and of course, this is not sustainable. And I think it would be naive to think that this will continue, or we will be able to reach these levels of installed capacity of wind with this approach, which means that we need to move to a more efficient use of the electrical infrastructure offshore, and hopefully move towards develop an offshore grid. And this slide shows how this can happen step by step, starting from the point-to-point connections. Like I showed you today, there are actually quite a few of those in Europe connecting two AC systems, and then adding a third terminal to that. I think this is, again, a third terminal. It's talking more about half bridge or full bridge. I will not go into the details, but in general, increasing the number of converters that can happen, going on what here it's called an offshore hub. So you have a concentrated infrastructure in the form of a hub, and this can connect multiple offshore wind power plants to multiple AC systems, and done that with multi-vendor. And very important thing when we talk about offshore grids is the fact that nobody will build a grid that is based on a single provider. Yes, only Hitachi ABB or GE or Siemens converters. So what we need to have is to be able to have converters from different manufacturers that can operate together. And I briefly touched upon it earlier that when we talk about converters, their control. I mean, converters are basically defined almost fully by their software, and a bit less by their hardware. So it's almost fully defined by their software, so their control. So to be able to get to this multi-terminal transnational offshore grids, we need to be able to solve the interoperability aspects, of the capability of the converters produced by different manufacturers to seamlessly work together. But I think if we want to try to reach the ambitions for offshore wind, we will definitely start seeing more and more shared infrastructure, so moving towards what we call an offshore grid, as opposed to point-to-point connection today. Then very briefly, why offshore grids? I think it's very intuitive that it will reduce the cost, reduce the capex and opex, and I think there is a study in UK done by I think not National Grid, of Ofgem. Anyway, a study that shows that actually an integrated grid design, offshore grid design, will reduce the cost by 18%, which I think it's very, very important, very significant. But also, as I said, reduce the environmental impact. We'll have fewer offshore platforms and converters. And of course, if we move to a meshed grid where you have multiple paths to deliver the energy, that will also increase the availability and reliability of the overall system. So there are quite some important advantages in building the offshore grid, but we also have some barriers. I think today is that there is still a limited market. There the projects that are happening are very, very large, both in terms of capacities, but also in terms of cost. But there are few projects, so it's not very easy to develop very fast for the different producers, because they are very large and few projects. And then, as I said already, the HVDC converter interoperability is very important, because basically, and I'm oversimplifying a bit, but basically control is the main IP for the vendor. So the producers of the different power electronics, the way they are controlling it is their main IP, and that they are very reluctant to share it with or share too much details about it with their competitors. And of course, aspects related to the components, the DC breakers, I didn't say anything about it, but this used to be one of the big bottlenecks in developing offshore grids, but I think we are almost there. And then, of course, parts that are less technical, but very, very important when we talk about regulatory and legal, because as you see, we have hybrid and transnational assets, which is not, the current rules, I think, basically say that each asset belongs to a country, while now we will have assets that are connecting and in a way, belonging to more systems. And of course, an operational one, if we have this large development, an offshore grid, is that we can still operate with each national TSO being in charge. I think that is the model today. Each country, the TSOs in the respective country is also the one in charge of the offshore grid. But in the future, I'm not sure that this will be a way to continue. So maybe an offshore TSO or a higher structure like in the US on top of that, a system operator might be created. So there are still barriers to overcome, but I think the direction is clear that we are moving towards the development for offshore grids, at least in Northern Europe. And finally, I touched a bit about it, but you probably heard by now that the energy island concepts, that it's been discussed for a while between the Dutch and German TSO TenneT and Energinet in Denmark, but now actually last year the Danish parliament decided to build those two energy islands in Denmark, one of them in the Baltic Sea in Bornholm and one of them in the North Sea, and both of them will be connected to other countries. So they will, at least when they are built, they will be the first example of this multi-terminal transnational grids, DC grids that I was showing you earlier. Yeah, and they will have the one in the Baltic Sea is 2 gigawatts, but the one in the North Sea is going to have a 3 gigawatts installed capacity initially, but then it should be able to be expanded to 10 gigawatts by 2050, which I think it's already very, very large. If completed, or when completed like that, it's probably going to be the largest power plant, if you see it as a single power plant in Europe. So very important projects. The one, as I said, the Baltic Sea Energy Island will actually use an existing Bornholm island. We'll use that island as where the infrastructure will be placed, and it's expected to connect it, of course, to the Danish mainland grid, but also maybe to Poland, Germany, and Sweden in the near future. And of course, at least the connections to shore will definitely be HVDC for different reasons. One is because Denmark is a different synchronous areas than the continental Europe, but also the distance is fairly large between Bornholm and these countries. And this one, I think it's expected to be built by, I think it will be tendered this or next year. I think the requirements will be specified, and then it's expected to be built before 2030. And as I said, this could be the first transnational multi-terminal DC grid. And if you want to read in the promotion project, the partners, we did a pre-feasibility study about this connection. And already Energinet and 50 Hertz have signed an agreement and memorandum of understanding to study the construction of an electric cable connection between the two countries via Bornholm. So I think this has very good chances to happen in the near future. And if we want, just very briefly, I see time is running, I'm sorry for that, but very briefly, when we start building it or looking at the topology, we have some choices to make. It can be either a DC hub, so even the offshore wind will be connected via DC, or it can be an AC hub where you have the offshore wind connected to an AC to the onshore grid, and then you have the HVDC connections to the different AC systems here shown between Denmark and Poland, and you can see that there are separate connections to the respective countries, and this is done because actually one of the main constraints is the way we are operating the onshore systems. For DK1, for example, the maximum loss of infill, so the N-1 criteria for the stability is 600 megawatts. So if we build 2 gigawatts of offshore wind and we try to connect it to the main AC system, we need to do it in a way that we will not lose more than 600 megawatts at one time. And of course, this has an impact on how to build the interconnection, both in terms of ratings, but also if you're going to use metallic return for each connection or only for some of them. So of course, it's not as simple. These projects are one of a kind, and they are unique, and they're gonna be the first of their kind in the world when they are built. But still, very exciting developments, I think, for offshore grids. And then finally, if we think about the about the energy islands or hubs, as you want to call it, because the Bornholm one, it can be a hub, not necessarily an artificial island, but they are, I think, a big step forward in development of the offshore energy infrastructure. And not only because if you think a bit about them, they are 100% inverter-based systems, since they are DC connected. They have basically no inertia in their system, very low system strength, which are only inverters, and they're going to be multi-vendor environment, both production and maybe some demand in a more medium term. If we look at them, if you have power to X, electrolyzer, or other things there, and of course they have to be built already today, or when they are designed. When I say today, in the near future, to be able to be robust and seamless expansion, because nobody will accept, for example, to stop operating the initial energy island for a couple of years because it needs to be expanded. So I think, as I said, the electrical design and the operation of such an energy island is a challenge never done before. But always from the challenges, it's also moving things forward and pushing things. The development of things is where we learn more. And in many ways, I think that the future energy hubs are versions of the hopefully 100% inverter-based systems, which if we continue the decarbonization of the power system, we will probably get to that or very close to that if we still have hydro, for example, in the system. So the energy islands, I think they are exciting both from an offshore grid development perspective, but also from the lessons that we can learn from it, looking into the future and in this fantastic transition that we see in our power and energy systems. And finally, the summary, I will not read that again because I think it's basically the main points that I hopefully try to convey to you today. So I'll stop here, and I hope I was not too fast.
I don't know. I am always amazed how fast you can speak, and it's amazing. I mean, you have talked for 1 hour without break, and very fast. I mean, my brain is challenged follow all the details, but it has been amazing how comprehensive and how many different perspectives you have touched. So we have time for 1 or 2 questions, please, from audience. You should be very, very fast. Okay. Nobody. Yeah, I have some few questions, but I wasn't so fast as to write them down. Yes. Yeah. Just I was just thinking about this Horns Reef wind farms. Do you know, are all of them radial? Also the Horns Reef third, or
yes, I think so. Okay. I think they're all Horns Reef 1 and 2 definitely, but I think also yes. Horns Reef 3 is a radial connection.
Okay, because I was wondering on the last one. And then I was thinking that you have been through all this HVAC, HVDC connections, and at the end you talk about a bit about this combined connection, hybrid connection concept. Can you very quickly elaborate a bit about on, I mean, of course, all of them, they have advantages and disadvantages, but do you see in the future that hybrid concept will overtake, of course.
I'm not sure which one you mean hybrid.
The combined one, so the Kriegers flak, right?
Okay, the Kriegers flak is yes, they call it the combined grid connection because it combines the connection between Denmark and Germany and connection of offshore wind. So I think that in many ways that project will be one of its kind because it has some very specific characteristic in that area because some of the wind farms were already existing there. So the German side there was already 1 or 2 offshore wind farms, so they were already existing and connected to shore and having their AC connections to shore. So moving to DC HVDC connection would probably mean too many changes. But I think moving forward, honestly, I do think that the DC technology will prevail. The HVDC technology will see more and more of it because it has many advantages, more stability. I think this very long submarine AC cables and very complex infrastructure, AC infrastructure, is raising a lot of challenges: resonances, harmonics, transient events. We've seen, sometimes they react in an unfortunate way when they have grid faults. Yeah, I think it happened in UK a couple of years ago where we had that partial blackout. So I think in many ways DC technology we will see more and more of the DC technology in the future.
Thank you. So no questions from the audience?
Well, you have the recording, so if I went too fast, maybe you can slow it down, and you are of course always welcome to contact me or send me any questions you want, and I'll send you the slides, of course.
Yes, thank you. One more time.
Can I jump in with a question if that's possible?
So, yes, Damian, please.
So Nikos, a very, very interesting presentation, and as Anka said, you covered a lot. The word hydrogen keeps getting mentioned more and more. I wonder what your thoughts are on sort of doing away with these HVDC connections and perhaps using hydrogen as being the carrier of the energy from the wind farms in the future.
I think it's very hard to say. I think hydrogen has potential. It came up quite suddenly in a way as an alternative energy carrier, but I think maybe in some future it will make more sense to not transfer electricity to the shore, but transfer it in the form of hydrogen. But I think for quite some period now, electricity is more flexible and it provides quite some advantages already in the infrastructure, and I think it will still be the main way of transporting the kinetic energy from wind to get it to the shore via electricity. So I think, if you want my personal opinion, first we should electrify as much as possible or everything possible, and then have hydrogen as an energy carrier for the areas where electricity is not very easy to penetrate. But in a very distant future where we have wind power plants which are very far from shore, floating and very far from shore, we may reach a point where it would make more sense to have hydrogen and transfer that or transport that hydrogen to shore via pipeline. But personally, I think we should stick with electricity, at least for the foreseeable future.
Okay, thank you for that. It's good to know that none of us are out